Good morning, Professor, and welcome to our presentation of our assignment 2 for algorithm analysis. My name is Yuan Xing, and I'm joined by Clifford, Jun Kang, Ricky, Solomon, and George. Together, we are Team 12. So, today we'll be covering a few key aspects, namely the features our program has and how to use it, some information about the algorithms used in the implementation to achieve these features, as well as observations, reflections, and potential improvements that can be made to our program. So now I'll be handing over the time to George, who will run through the program and its features.
Oh my god. Okay, thank you, Yanxing. Okay, so this is our editor, and now I'll load an image. So let's say I load this clock. You see like all these windows appear, and you can actually control them via the checkboxes in the window manager. Okay, to show all of this nicely, I will reduce the scale first, something like this. And now I'll start the seam carving. So let's say I want to carve based on the grid, let's say dynamic algorithm, and then I put like target width to be this and target height to be this, and carve. Here you see like all of the seams that have been carved for the current carve, and here you see the resultant image. And now I'll go over the greedy algorithm and maybe set it something like this. And we can also set a delay for each seam to more clearly see the seam carving in action. So let's say I put something like maybe 70. So this is like the amount of delay in MS. Let's carve. And you can see that it's much slower now. So next is our graph cut. We have implemented graph cut, but because of the library we're using, it takes very long. So I will only set the target width to be like a little bit less. And let me carve this. And you can actually see in our profiler that like each seam is taking like a very long time to carve. Yeah. Okay. So that's done because I was only carving like 2 pixels. Yeah. And this is probably due to the library because our code looks correct. Now I'll go over the object removal. So let me choose another image to load. You can also like delete and load it back. Yeah. Okay. So now I will also remove this all seam since it's not very useful to show, and I'll attempt to carve out this guy. So just give me a moment while I carefully carve this guy out. Okay, now I'll pick object removal, and actually there are also 2 parameters that you can adjust, which is threshold as well as the aggressiveness, but we'll leave it at this because it's like a nice value that we have found. And let's carve. And you guys can see that the carving actually stops once the guy has been removed. So let me just make that a bit smaller so you can see. And now I'll demonstrate another example with this family over here. Okay, let me reset this first. Unfortunately, every time you do the object removal, the image will reset back to the original image. So you can only remove object once. Okay, let's try this again. Oh, I forgot I didn't see the guy over here. So my original image wasn't including the guy. Yeah, but but like most of the family has gone, and the image still looks intact. Now I'll go over another example of our object removal, but now you can clearly see that our object removal is smart in that it knows when to use horizontal versus vertical seam carving. So let's just carve this. So as you can see, if the object is like this sort of like horizontal in shape, it will use the horizontal seam carving, whereas if the object is vertical in shape, it will use the vertical seam carving. You can also save images that have been carved already. So let's say I save this as carved. You can choose the extension. Right now I'll just use PNG. I can double click this image to open the new carved image. Okay, now I'll pass my time over to Ricky, who will go over the dynamic programming.
Thank you, George. So now I'll be going over the dynamic programming implementation. So to summarize, what we do for dynamic programming is to calculate the energy map, and from there calculate the cumulative energy map, find the seam, visualize the seam, and then remove the seam and resize the image. So going more in depth into how we calculate the cumulative energy map. After we got the energy map, we will start from the second last row and try to find the cost of the total path to reach each column. In our examples for this presentation, we will be using vertical seam carving. So for example, taking this node with this column with value of 4, the possible paths to get to it are from 6 and 5. So the lowest possible total cost will be 9, as it goes from 5 to 4. Therefore, we store 9 in the corresponding column of the cumulative energy map. Then we repeat this for the other rows. Like for example, for this, in this case is 7. The possible paths are from here and here. Therefore, the cumulative energy map will show that the value is 12, since the lowest possible path is to use the one with the previous row of value 5. Now we'll move on to find the seam. So to find the seam, we begin from the top of the cumulative map and search for the column with the lowest value. In this case is 8. Then we move on to the next row at the bottom to look at the nearby columns. In this case is 6 and 10, and then take the lowest possible one. So in this case it will be 6, and continue the process for the remaining rows. So for this third row, the nearby columns will be 4, 7, 8, like this. Then we'll take 4, and this is how the vertical seam is generated. Now moving on to the greedy algorithm, it is quite similar to the dynamic programming approach, except that we don't use the cumulative energy map. So we find the seam in a similar manner. However, we can start from the first row or last row, and regarding both of these, the results may vary. So starting from the row, from the last row, we begin searching through the entire last row for the column with the lowest value, then looking at the nearby columns in the next row to search for the lowest value between the nearby columns. In this case, it will be 3. These are the nearby columns. The process is repeated for the remaining rows. A quick comparison between the greedy algorithm and the dynamic programming approach is that the greedy does not always find the global minimum. This is shown in the blue arrows in this diagram here. As you can see, the greedy approach uses 4, 10, and 1 for a total of 15, whereas the dynamic programming approach takes the blue arrow and uses 4, 10, and 1, which gives a total of 15, whereas the greedy approach uses 4, 2, and 10, which gives a total of 16, which is not the global minimum. Therefore, the images tend to be slightly better in the dynamic programming approach. Next, Clifford will be talking more about the graph card.
All right, thank you, Ricky. So as mentioned earlier by George, we managed to implement GraphCut into our program. But before we talk more about that, let me briefly explain what GraphCut means. So GraphCut, as the name suggests, partition a graph by cutting the edges of a graph. So you can see in the example on the right, the diagram, we have a graph that has A and B, and by carving it, you'll be essentially cutting these edges. Well, I think I missed one of the edge here, but okay. So anyway, you're interested in GraphCut. You're interested in actually the cost of the cut. So in this example, the cost will be 3, 6, and the sum of 3, 6, and 8, which will give 17. So this brings me to the point of what max flow and min cut is. Min flow and max cut is. So max cut represents like the cut that generates the smallest total cut among all the possible cuts. And some well-known algorithm that implements max cut is Ford-Fulkerson and Edmund-Karp. So in the context of seam carving, we are currently using a library, MaxFlow by Boykov, and a node will represent a pixel, and the edge weight will represent the energy through a pixel. So in this example, you can see right here. So let's take an example of like a vertical carving where we want to find a vertical seam. So firstly, you'll start off by connecting the first column to the source and the last column to a sink. Then by calling the MaxFlow function in the library, you'll generate a 2-segment of the graph. And as you iterate through, like let's say the pixel, the first node that you find that is a sink will be part of the seam. So by doing so, you'll get all the different seams that will generate. You'll get all the different pixels that will generate the vertical seam. So now Solomon will share more about what the object removal in our program.
Hi, so now I'll be moving on to the object removal. So given that we have this original image on the left, and then if we were to outline the human in the image will be, the object will be removed, which is the human, and this is the result. So what it happens is behind the scenes is that after you outline an image, it computes the max length of each layer in the mask and compare with the height. And it chooses the one which requires fewer seams, and it iteratively removes seams through the mask area. So now I'll be passing my time to Jun Kang to talk about the time and space complexity.
Thank you, Solomon. So first we'll be looking at the time complexity for both algorithms. So for the dynamic programming, we can see the time complexity written on the right of the table and the process written on the left of the table. We can see that the growth rate tends towards OWH, W being the width and H being the height of the image. Moving on to greedy algorithm, you can see that it's almost exactly the same as before, with the exception of calculating the cumulative map. Moving on to space complexity, we see that both dynamic programming and greedy algorithm uses the matrix of the energy map, which is the width times height, and dynamic programming uses an additional matrix for the cumulative map. The overall space complexity is also the same of OWH. Now moving on to a reflection for this assignment, we can see after doing the assignment, we see that both have the same time complexity when it comes to seam carving, but because of the algorithm, dynamic programming has better output when carving the image. There are some improvements that we can also make to our program by not recalculating the energy map every time we move to the next iteration, whereas only calculating the affected pixels. That's all for our presentation. Thank you.